In this example, we will evaluate the definite integral from square root 2 to 2 of the function 1 over x cubed times root x squared minus 1. Now, looking at the form of our integrand, seeing that expression x squared minus 1 inside that square root, that's a really good indicator that we should think about applying a trigonometric substitution. The desired trigonometric substitution would be x equals secant theta. So that dx is equal to secant theta tangent theta d theta. But a very important thing to keep in mind is because it's a definite integral, whenever we apply a substitution, we do need to change our limits of integration. So we need to think if x is equal to root 2, our lower limit of integration, what theta value does this correspond to? Well, this would tell us that square root 2 is equal to secant theta, and secant theta is 1 over cosine. So 1 over root 2 is cosine, so we have theta is equal to pi over 4. In a similar perspective, for that upper limit, x equals 2 would imply that 2 is equal to secant theta, or that 1/2 is cosine, so that theta is pi over 3. So now in terms of an integral only involving thetas, we have a definite integral going from our lower limit of integration, pi over 4, to our upper limit, pi over 3. We replace every x with a secant. So 1 over secant cubed theta multiplied by the square root of secant squared minus 1. And then the dx becomes a secant tangent d theta. And now that we've applied our trigonometric substitution, we rewrite the integrand via the desired trigonometric identity. Well, secant squared minus 1 is tangent squared. So if we do a few simplifications here, we have a secant theta in the top and a secant cubed in the bottom. So that 3 will be canceled and become a 2. We also have the square root of tangent squared, which is tangent in the denominator, and a tangent in the numerator. So the square root of tangent squared cancels off with the tangent, which is in the top. So what we are left with is the definite integral from pi over 4 to pi over 3 of 1 over secant squared. Well, 1 over secant squared is simply cosine squared theta d theta. So the nice thing about dealing with the definite integral is now that we've applied the substitution, we've changed our limits of integration, and this is an equivalent definite integral. So whatever value we come up with is going to be our solution. We don't have to do anything regarding resubstitutions. So let's just go ahead and anti-differentiate. In order to do so, we use this half angle formula for cosine. So this would be a 1/2 that pulls out front, because cosine squared is 1/2 times the quantity 1 plus cosine of 2 theta. The antiderivative of 1 is theta. The antiderivative of cosine 2 theta is 1/2 sine 2 theta. And this all needs to be evaluated from pi over 4 to pi over 3. So substituting in pi over 3, then we put a minus sign and we plug in pi over 4. So 1/2 sine of 2 times pi over 4 would simply be pi over 2. And keep in mind, whenever we're evaluating a definite, or whenever we're evaluating a function and we have this common value, we should go ahead and simplify. So recall that sine of 2 pi over 3 is the number root 3 over 2, and sine of pi over 2 is the number 1. So putting this all together, I'm going to go ahead and just leave the 1/2 out front, but we'll have pi over 3 minus pi over 4. That's pi over 12. Then we have plus 1/2 sine of 2 pi over 3, so 1/2 times root 3 over 2. Then we have minus 1/2 sine pi over 2. So let's just do minus 1/2. And this number, whatever it might simplify down to, is the solution. It gives us the value of this definite integral. So once again, to reiterate, whenever we apply a substitution, in this case a trigonometric substitution, to a definite integral, we must change our limits of integration. But the upside to doing so is that we do not have to draw a right triangle here to resubstitute. We just evaluate the resulting definite integral.